So just we have seen about the optimum filter, how to maximize SNR by using the optimum filter. We have seen how we will get the optimization parameter, and that will depend on the different signal, not on the individual signal. Then we have seen how to calculate its transfer functions of the optimum filter. And here we have seen when we are finding the transfer function of a filter which will meet the criteria of maximizing the ratio, because here we are supposed to maximize the ratio. At that time you will get its probability of error will be less. So to maximize the ratio, we are increasing rho equal to, we are taking S01T minus S02T upon sigma naught. So if we are increasing it, you will get probability of error will be minimized. So here now we are supposed to see about the match filter. So in the last session when we have seen optimum filter, at that time that was generalized Gaussian noise, and you will get the optimum filter which will maximize the ratio, and you will get what you are getting the parameter, you are getting gamma max square equal to integration minus infinite to infinite pi of f square upon gn of f of df. So here we can say if we are using the optimum filter which will increases the maximum ratio, at that time input noise is wide Gaussian. If input noise is wide Gaussian, at that time you can say that as a match filter. So here in today's session we are supposed to see about the match filter. So here we can say if the signal S of t gets corrupted by additive wide Gaussian noise, the optimum filter with impulse response match filter to maximize the output signal to noise ratio. And if we are using here that optimum filter which will give us maximum signal to noise ratio, but if input is a wide Gaussian noise, we can say that as a match filter. So we can say this optimum filter we can call as a match filter, and its power spectral density of wide Gaussian noise, if gn of f is equal to neta by 2, you will get its transfer function as h of f equal to k into complex conjugate of pi of f upon neta by 2 into e to the power minus j 2 pi ft. There are number of equations. You are supposed to see how we are taking the transform function. So here we are saying if we are using the optimum filter which will give us maximum SNR when input noise is Gaussian, we can say that as a match filter. So for additive wide Gaussian noise we are supposed to take, we can say Gn of f or we can say Sn of f, that will be equal to n naught by 2. So here you will get h of f equal to k into, you can take pi of f or you can take g star of f in upon n naught by 2 or you can take neta by 2 into e to the power minus j 2 pi ft. Now we are saying that as a transfer function of the match filter. Now we are supposed to see the impulse response of match filter. How we are taking? If we are supposed to take the impulse response of filter, we can take its Fourier transform. Inverse Fourier transform. So we can take f inverse of h of f. So you will get that will be in the integration form. So you will get 2k upon n naught or you can say 2k upon neta into integration minus infinite to infinite. We are taking here p. You can take g or you can take p. Only you are supposed to understand what terms we are using that. So we can take here 2k upon n integration minus infinite to infinite pi star of f into e to the power minus j 2 pi ft e to the power j 2 pi ft df. So you will get that as 2k upon neta into e integration minus infinite to infinite pi of f into e to the power minus j 2 pi f t minus 2 df. So if you solve, you will get its h of t equal to 2k upon n. 2k upon neta. That is nothing but that is not efficiency. That is the noise. We are taking as the noise parameter n naught into S1 t minus capital T minus t minus S naught t minus t. So here we can say you will get, so here now we can see about the probability of error of the match filter. So from the Parseval's theorem we are taking integration minus infinite to infinite p of f square df equal to integration minus infinite to infinite p square t dt equal to integration 0 to tb p square of t dt. So here if we are saying pt will exist for only time 0 to tb. Now from the expression of optimizing parameter of the optimum filter, we can take optimization parameter sigma max square equal to 2 upon, you can take n naught or you can take neta into integration minus infinite to infinite s1 of t minus s naught t square dt. If you put the value of s1 of t and minus s naught of t here, you will get, our equations will become, if you are solving a minus b square, you will get s1 square of t plus s naught square t minus 2 s1 t s naught t dt. If you are taking that as the energies of s1 of t s naught of t, you can write 2 upon n, 2 upon neta into es1 plus es0 minus 2 es1 S0. So we can say ES1 and ES0 are the energies of S1 of t and the S0 of t respectively. So you will get ES1 S0 is nothing but it is the joint energy of the product waveform. So here when we are taking S1 of t equal to minus S0 of t, you will get ES1 equal to ES0 equal to minus ES1 S0, and if you solve you will get the parameter, optimization parameter for the match filter, that will be equal to 8 Es upon neta. There we will get question numericals on the match filter, optimum filter. They will give you question and they will give you some values. You are supposed to use sometime the equations for probability of error, sometime impulse response of the match filter. Sometimes you can use the optimization parameter, that is nothing but sigma x square. They will give the some values and one unknown value. You are supposed to solve that numerical and you are supposed to find that value. So here if you are taking the value of optimizing parameter from the equation 3.35, you will get probability of error from equation 3.16 and 3.19. Here we are solving how to take its probability of error, which we have seen in the optimization filter. Now we are supposed to solve for the match filter, when that noise is nothing but AWGN noise, additive white Gaussian noise. So here when we are solving its probability of error, you will get P of E equal to 1 upon 2 ERFC, P naught T upon 2 square root of 2 sigma naught. So if you are putting the value, if you are solving that, you will get 1 by 2 ERFC. We can take here P naught square of T upon sigma naught square. You can write as a gamma square. That is nothing but the probability, the optimization factor, optimization parameter. So you will get probability of error P of E equal to 1 by 2 ERFC gamma square upon 8 raised to 1 by 2. From the basic concept of the optimum filter, probability of error is minimum when we are taking gamma square equal to gamma max square. So you will get probability of error minimum equal to 1 by 2 ERFC ES upon neta raised to 1 by 2. So that equation will signify that error probability depends only on the signal energy, not on the signal wave shape. ES is nothing but signal energy. So here you can see probability of error probability will depend only on the signal energy. It is not depend on the signal shape. So if we are taking one example, you can see here. A binary baseband digital communication system will employ the signal, that is S of t, equal to 1 upon square root of Ts, where t value is in between 0 and capital Ts. Otherwise, its value of signal will be 0. So here we are supposed to determine the output of match filter. So to get the match filter output of the signal, input signal is convolved with the impulse response of the match filter. And how we are calculating the impulse response? You will get h of t equal to s of ts minus t with the filter constant part 1 and symbol for binary digit 0. You will get y of t equal to integration minus infinite to infinite s of lambda h of t minus lambda d lambda equal to integration minus infinite to infinite s lambda s ts minus t minus lambda d lambda. So here we can say the time reserved and delayed s of t will extend from t minus ts to t, and out of this range the integrand is non-zero for 0 to t on the region t will be less than ts for t minus ts. So 2Ts in the region T will be greater than Ts. So if you solve here, you will get y of t equal to T upon Ts if T value is less than Ts. And you will get y of t equal to 2Ts minus T upon Ts if T value will be greater than Ts. You are supposed to draw this waveform. Match for the rectangular pulse. So we will get here, this is the double slope triangular waveform as shown in above waveform. You will get at t equal to Ts, the output of sample is 1. You can see here when we are taking t equal to Ts, you will get output is exactly at 1. So we can say output sample will be at 1. Therefore, the general response of match filter you will get as y of t equal to integration 0 to t s of tau s of ts minus t plus tau d tau. We are saying that as the autocorrelation function of the signal. Now we can see the some properties of the match filter. If we are saying here, we can see here, in the operation and the principles, match filter act on the basis of simple unique some properties. We can see first property. If signal S of t gets corrupted by AWGN, the filter with the impulse response matched to S of t maximizes the output SNR. So here this property can be justified by considering a received signal R of t consisting of signal S of t and 0 mean Gaussian noise NT. R of t equal to, we can take S of t plus NT. So here when we are saying a signal gets corrupted by AWGN, the filter with impulse response to maximize output SNR, we can say this property can be justified by considering a received signal R of t consisting of signal S of t and 0 mean AWGN. With power spectral density, we are taking power spectral density N0 by 2, or you can take neta by 2. They will give the value, mostly they will give the value for that. If R of t is passed through a filter with impulse response H of t, we can take its filter output that can be sampled at Ts can be written as y of t equal to integration 0 to t equal to Ts R of tau H of t minus tau d tau. That will be equal to integration 0 to Ts s of tau h of Ts minus tau d2 plus integration 0 to Ts n of tau h of Ts minus tau d2. So here you will get y of t equal to y of s ys of t of s plus yn of t of s, where y of s, t of s and yn of t of s are the signal and noise component of the filter output. So we can say here we are supposed to take here SNR maximize. So there is a problem to select filter impulse that will maximizes the output SNR. That can be defined as SNR equal to ys of square of Ts upon Es ys of n square Ts. You will get here energized signal E of y square yn of square of Ts equal to double integration 0 to Ts E of neta E of n of tau n of t h of Ts minus tau h of Ts minus t dt d2. If you solve, you will get that will be equal to power spectral density neta by 2 into 0 to Ts integration h square of Ts minus t dt. So we can say if we are putting the values of noise variance from equation 3.41 into equation 3.40, you will get signal to noise ratio will become equal to 2 upon neta power spectral density into integration 0 to Ts s square of t dt. So you can take that equal to 2 Es upon neta. So here we can say from the squares inequality you will get the maximized value of SNR. So here we can see the second property for the match filter. This will tell us that the impulse response of the match filter is the mirror image of the signal. So here from the Schwarz inequality it is easily understandable that impulse response of match filter we will get as h of t equal to k into s Ts minus t, when t value will in between 0 to Ts, and at that will be equal to 0 otherwise. So we can say this will implies that impulse response of filter is responsible for maximize the signal to noise ratio, and that will be the mirror image for the message signal, which will be delayed by symbol durations. Now we can see the third property for the match filter. So here we can say the match filter does not contribute any intersymbol interference. So for the delay, Ts and the convolutions operation, the match filter output is always non-zero if T value will be greater than 2 Ts. So we can say match filter will introduces a delay but does not introduce any intersymbol interference, as it makes the output to go to 0 at the next sampling instant. So here we have seen the properties of match filter, which will tell that the spectrum of output signal of match filter with match signal as input is proportional to the energy density of a input signal. So you will get here as signal to noise ratio maximize equal to 2 upon neta power spectral density integration 0 to Ts s square of t dt, or you can take that will exactly equal to 2 Es upon neta. Again we can say the output signal of match filter is proportional to the shifted version of autocorrelation function of the input signal to which filter is matched, because here we are saying the impulse response of matched filter is the mirror image of signal. So you will get h of t equal to k into s of t of s minus t when t will be in between 0 to Ts. Otherwise its value will be 0. And third property will tell us that the impulse response of match filter will does not contribute any intersymbol interference. So here we can say the output signal to noise ratio of match filter will only depend on the ratio of signal energy power spectral density of white noise at the filter input, and these are the properties for the match filter which we are supposed to use when we are supposed to improve signal to noise ratio. Remaining we will see in the next class. Thank you.